y'all doing today? My name's Jason. Introduce you to our project, A.L.I.A, Autonomous Line Inspection Assistant. So San Diego Gas and Electric has been approved by the FAA to conduct testing using unmanned aerial vehicles to inspect power and transmission lines. So the use of these unmanned aerial vehicles has two main benefits. First, it'll reduce line worker hours. It'll also increase their safety so they're not climbing poles. So in order to accomplish this project, we bought an off-the-shelf fly-capable UAV from 3D Robotics called the X8 Plus. We outfitted it with two main payloads, an observer map payload and also a current sense clock payload. And using these payloads, we accomplished three distinct missions. An observation mission, we can look at the power line, observe around the power lines. A mapping mission, we create topographic maps of the area surrounding the power lines. And a current sensing mission, which we sense the current on the transmission. So our first payload is the observer map payload. This has a GoPro Hero 3 connected to the quadcopter via a gimbal. The gimbal is basically a stabilization device to stabilize our video, and it also allows us to change the orientation of the video. And this is fed through a 5.8 gigahertz main video feed into our ground station. Next, we have a Lepton long-wave infrared sensor, which is fed into our ODroid. And from the ODroid, we send it through our secondary video feed to our ground station. And lastly, we have a LiDAR radar rangefinder. We use this for object avoidance as well as the distance to the ground. And this is fed into the I2C bus of our quadcopter, where it can be viewed in the telemetry data. And I'll pass it off to Mark for the next slide.
All right, in the observation of our observer map payload, we can locate and record objects of interest. We can record these objects in HD locally and stream low resolution video in both color and infrared. Devices included into this payload are a GoPro camera, which is attached to the gimbal, as shown above. The GoPro allows us to simultaneously record in high definition and low resolution first-person view and wireless stream. Telemetry overlays with the wireless stream to show important information such as timestamps and the recording. Infrared imagery is provided by the Lepton sensor through BSPI to our Raspberry Pi device, the ODroid W. Raspbian is the software used for the ODroid W. Next will be David to discuss about our mission planning software.
So Mission Planner, we'll be using it to control the craft and plan missions. Mission Planner is a community, open source driven software that we can plot, easy to use with a point and click. We can create a whole mission, such as this. I'm creating a few waypoints around. Because it's free and open source, we can also view and modify the source code. And some of the cool implementations we've been doing with Mission Planner is adding two video streams. We've added on this side a video stream of our GoPro Hero 3 mounted on the copter in front, so you can see a first-person view. On the right side, we have our Lepton camera view, so you can see a good heat signature of the power line and see if there's any hot spots along the power line. We also added a new tab for the current clock, so we can display the current values being read from our current clock off the transmission line. On the right side of those arrow keypads, we've been able to use it to control the craft strictly through Mission Planner. So we don't have to use it through a RC remote control. We can also use Mission Planner to control the craft and where it goes. And then pass it off to Daniel to show off power inspection line.
Our main goal with HD video was to achieve high enough resolution that we could detect damage on a simulated power line, which we did here with frayed wires and rust red paint on a bucket. As you can see, the GoPro Hero 3's HD capabilities were more than enough to satisfy this goal. And with the thermal camera, we needed to be able to detect sizable temperature differences. So you can see here when the bottom of the bucket is black, that's when we had ice sitting at the bottom to show the difference. And when the bottom of the bucket is a bright yellow, that's when we had coal sitting at the bottom to simulate a heat spike in a damaged transformer. And now Chris will tell you about the LiDAR sensor.
All right. Our LiDAR sensor, which we use for object detection, one of the ways we will be using it is to do a horizontal sweep. And with this horizontal sweep, you can see that it's detected objects at various distances. Its maximum range is about 40 meters with a resolution up to 1 centimeter, and it samples at about 1.5 hertz. This LiDAR will be mounted on the nose along with the lepton, and this nose mount will be adjustable, so it can actually face forward and face down depending on the mission. And I'm going to pass this off to Body G with communications.
All right. So I'll just talk about the database we're using. So SDA-G&E uses a database called the A.L.I.A system, and it's used to keep history of various values to make sure each component is operating correctly. So this database consists of a point and some value attached to it, and we can store various data onto the server. So some of the data includes GPS locations, altitude, longitude, latitude, and heading, and various other data. And using Mission Planner, we wrote some additional C# libraries to communicate with our Pi server to allow us to create points and update those. So here we see the interface for a software called A.L.I.A System Management Tools, and this allows us to search and look up values and to make sure they're created and updated correctly. So over here, so for one mission that we flew on April 21st, we created a point called to store altitude, and you can see when the point was created and that it's updating every 10 seconds. And we can store various other data and make sure, or we can easily look them up for each mission. As for, we also designed a case to all our various components, such as our router, our C controller, ground station, and various other cases. And this makes it easy for the line workers to set up the ground station and power up various devices. Now I'll pass it on.
Thanks, Body. So one of the new exciting things that UAVs have been useful for is actually mapping. So we thought this would be handy for San Diego Gas and Electric, not only for property management, but also disaster relief. You could map out a fire line or recreate a landslide that possibly happened during a flash flood, flash flood event. So the purpose of this mission is to fly a grid pattern that we want to survey autonomously and then collect HD imagery from that and be able to reconstruct it, render it into a 3D model. So Mission Planner is how we'll accomplish the auto waypoints and the grid. You define the grid and it actually maps out the waypoints. You can set settings for image overlay if you put the focal length of the camera and the resolution of the imagery. So there's a lot of support for that. And as the quadcopter finishes its mission, you can see the time-elapsed photography that's collected with the GoPro. So taking that data, we can use a software called Visual SFM, or Visual Structure from Motion, that actually finds pixels that have matched in the individual images and reconstructs it into 3D. So you can see the flight path of the quadcopter in each of the individual images that is then reconstructed to show that that's the perspective of that image. On top of that, we can also audit it with the LiDAR because we have GPS and timestamps, and that's all searchable through the OSI-Pi database using through the telemetry logs. So these are the results of two different mapping missions. They're actually 3D models. Unfortunately, the 2D doesn't do it justice, but you can easily see vegetation, the inclines and the canyons. This is a canyon in Blacks Beach, and then that's Harry Griffin Park, which is close to Grossmont High School. So it's really amazing. You can reconstruct the field, the paths, the trees, the bushes, all just from HD imagery. So that concludes the mapping mission. I'm going to hand it over to Alejandro. He's going to talk about the cloud.
Hello, so this is our current Sense Cloud mission, also known as CSC payload. This is our last mission and our second payload. The CSC mission, also known as the cloud, requires us to attach the cloud to the power line, and we're also magnetically detaching it once it hits the power line. We're also measuring currents using the claw and would wirelessly transmit it back to the ground station. So here's an illustration of our claw. Our claw has 4 magnets on the end of it, and basically that controls if it's going to be magnetically detachable. And we also implemented a laser and photoresistor so that we will have an automatic mode to control the open and shut of the clock. I will pass it to Jorge for signal diagram.
All right, thank you, Alejandro. So this is our current ammeter. We designed one from scratch using a Hall-effect sensor, a toroid, PIC microcontroller. It's basically the brains of our current sensor. We're also using a filter to amplify the signal. In addition, we're using an amplifier to amplify the signal and a Wi-Fi communication to transfer that current data down to the ground station. In addition, we're using the laser actuated servo to automatically open and close or close the claw once it detects the power. And before I go into further into the claw, I wanted to go over it's a Hall-effect sensor, a toroid. A Hall-effect sensor is basically a device whose output changes in the presence of magnetic field. And a toroid is a donut-shaped object that allows magnetic field to form around them. And we bought a sheet of cold-rolled steel at our local metal shop, and we cut some different shapes. As you see on the very, very far right, we have 3 toroids that we cut. And we experimented, and we found the toroid with the angle, which is the blue line, to have a greater sensitivity when detecting magnetic field, so we went with that route. This is our basic current sensing claw schematic. As you can see, we have the toroid core that is focusing that magnetic field into the Hall-effect sensor, and the output of that is fed into a decoupling stage to separate the AC signal from the DC signal, and from there it's fed into an amplifier where the signal is amplified, passed through a low-pass filter, has a corner frequency of about 122 hertz, and the output of the filter is fed into an ADC, and after the running, go to the ADC.
Okay, so after we get the 60 hertz signal from the low pass filter, we sample it to figure out our max and min peak-to-peak voltage. We have extra time to actually sample longer than normal because we only have to send the current about every second or so. So we wanted to be able to sample for at least 3 periods. Each one of our sample takes about 65 microseconds, and for a 60 hertz signal, it takes about 16.6 milliseconds. So we sampled approximately 768 samples for 3 periods. After we find our peak to peak, we throw it into a lookup table, which then will give us a value of our current, which then we send over a UART to our Wi-Fi module. Our Wi-Fi module is able to send a wireless signal or communication over Wi-Fi to a local area network. Our local area network workers then send it down to the ground station, in which we get a GUI to bring in real-time data and then plot it over a graph. So then we can go back and see the actual any spikes or any low current values on the line. And then our GUI also is able to shut and open the claw using buttons, and then also change it from manual or automatic. And then if our battery does go low, we do have a low battery indication. So now I'll switch it over to Craig for testing procedures.
So to test our claw on our quadcopter, we had to make sure that it was able to be deployed easily. So we constructed a mock power line to accomplish that. We also had to make sure it was reading current data correctly. So we set up a variable electric load and varied the amperage on it. And we were able to accurately monitor the current on it within 100 milliamps. So here's a couple videos of our deployment of the claw in flight. As you can see, it's able to detach fine. We have a wire connected to each leg, which then connects down to the base of the current claw. And then we have magnets that will detach. And we had to make sure that these magnets weren't too strong, so that if the quadcopter is pulling away, we don't want it to malfunction and not pull away correctly. And then we had to make sure they weren't too weak, so that if the quadcopter is flying too fast, that the current claw wouldn't fall off. On the right, you can see the CCD camera giving us a bird's eye view from the quadcopter. This allows the line inspector to be able to easily adjust over the line to be able to get the current claw onto the line. Here's our project plan over the semester. As you can see, we had testing and design earlier in the semester during March and April. And then in the final few weeks we've been able to finally test our delivery payloads and make sure everything's working correctly. Now I'll pass it off to Joanna, who will talk about milestones.
So in the past several weeks, we completed the following milestones to enable us to complete our project. For example, recording, using a mission center to fly autonomously and record the mission in HD was completed on the 4th of April. And then incorporating the LiDAR on the quadcopter and doing a successful flight test was completed on the 5th of April. Then we also had having the current app communicate with the Wi-Fi and send information to the ground station was completed the 22nd of April. And just recently we did a map mission where we reconstructed a 2D and 3D reconstruction of the Harry Griffin Park. So this is our cost analysis for our project, and to design and build the A.L.I.A, we spent $3,455 of our $3,500 budget. Our most expensive component was the X8 Plus quadcopter, which took 37% of our budget, including extra batteries and propellers. And then we also spent 25% of our budget on video transmission and first-person view components, including like an HD GoPro and a low-resolution CCTV camera, as well as transmitters, receivers, and polarized antennas. We spent 24% of our budget on the server map payload, where we spent money on the LiDAR and spent on the thermal camera, and spent 9% on the current sense pan payload, and finally we spent 4% on the ground station. As we have seen, our project includes two payloads: the server map payload, which checks for faults in power lines, monitors the temperature difference in transformers, and is able to map vegetation around power lines, and the current sense payload, which can send and save data, current measurement data. And our project also includes an integrated mobile ground station, which makes it easy to transfer objects or equipment from one place to another, and it makes it convenient to do testing outdoors. A.L.I.A autonomous line inspection assistant is a prototype drone that would facilitate the testing of power lines for line workers. This Friday, May 8th, we invite you to Design Day so you can see it firsthand and ask us any questions you may have.